Okay, folks, it's very, very early on Thursday morning, and I'm trying to record this in chunks. We had I found out not last night, but the night before, so Tuesday night, that someone that's in my son's class and their siblings are in daycare together, their family tested positive for COVID on a rapid. So obviously we stayed home yesterday. So I have my kids home all week. They had half of one day back because there was no buses and I still had to try to get to the school. Anyway, it was madness on Tuesday. Out of an abundance of caution, I kept them home yesterday and had planned to the rest of the week. Last night I didn't feel very well, and this morning my 5-year-old was vomiting. So he's back to sleep right now. He's snuggling with his dad. But every family I know in town that has small kids, it started with the parent feeling kind of a little unwell, and then the small child puking. Has been pretty much exactly how it's played out in all the families here, which means I know I have hours left until I'm a hot mess, and our whole family is a hot mess. Now, obviously I know that lots of people are going through this, but I have a lecture to record for you guys, so I'm trying to get through as much as I can. It's very early in the morning. I am a little bit out of it because I've already recorded some of this and realized I had made a mistake and wasn't doing things the way I would normally do. So I just deleted 30 minutes of lecture and I've started over just to keep my own head clear. So I was looking at what problems I had posted in the lecture and on the PDFs, and I decided the better one to go through was the practice review set rather than the project review. Both are there and worked out, but this one I find has a slightly better narrative, and it was purposely broken into chunks. So we can answer all the questions in fewer steps, really, and in some ways we can do kind of a beautiful progress. So this is the PDF called ARC2046 Additional Practice Problems. If you had previously downloaded it, there was an error in it, so re-download it while you're watching this video, because that means you have the latest and greatest version of it. When I came downstairs, I also found that my camera had broken, so I can't turn it back. The camera works, but the stand is broken, so I can't turn it back and forth to my face and the paper easily right now. I have it very precariously kind of tied off on the light, so that it's perched so that you guys can see the paper. After I'm done recording this, I'll go online and buy another stand, as this is the one I bought in September. So that's later's problem. So the very first question we're going to do is we're going to look at this king post truss. So king post has one post in it. This is a truss, which means it's an element in bending, but we've optimized its performance by putting everything in tension or compression. If you guys remember from last year, tension and compression was kind of easy to deal with. We had buckling in the compression side, but we had lateral torsional buckling in the bending side of it too. Actually, we haven't talked about buckling. We haven't talked about lateral torsional buckling much. So those are things we're going to solve in this term. So we have a truss, but we do know that when we were bending things, when we looked at my foam block, if there was a load going downwards, the top chord was often in compression and the bottom chord was often in tension, which made it kind of handy to just be able to check ourselves when we went through and solved some of these things. Sorry, I'm feeling worse and worse as this is progressing. So we know that we want this thing to be a structure to be static. Static means it's not moving. Not moving means the whole object isn't moving up and down, side to side, or spinning in space. We know that we had 3 equations to do that. If it's not moving up and down, or in the y direction, the sum of all the forces in the y direction must be 0. If it's not sliding back and forth, or in the x direction, the sum of all the forces in this direction must be 0. If it wasn't 0, it would move. And for it not to spin in space, the sum of all of the moments causing it to spin must be 0. Otherwise, it would be rotating in space. So let's take a look at this truss they've given us. They've said, okay, what we did last year is normally we were given a load and we were trying to find all of the internal forces in this object. It looks like here they've given us the internal capacity of this member, and they want to know what load we could apply to this. So this looks slightly different than we're used to, but let's just go through and pretend it's exactly the same as the problems we did last year. Don't let the slightly different information throw you off. We know that we can, if we take this and draw the free body diagram, which makes sure it's stable, and sum the forces in the y, x, and spinning, or the moment about z, we can figure out what it takes for this to be stable. We also know that we can cut any section of it. If the whole is stable, any component of it must not be sliding up and down, sliding back and forth, or spinning in space. That was called method of sections. We know we can then use method of sections to solve for internal forces. Well, they've already given us an internal force. So let's see what we can do with this following our old unique methods. If you look at the assignment set, or the solution set for this, I solve it in a different way than I'm going to right now. Both are correct. It's still all the same information, but maybe just a slightly different order that I do things. So what I'm going to do is I'm going to go through and start to solve this using the unknown PF as the applied load. So let me make this bigger. All right, so let's start solving this. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I always find it handy to redraw my object. Something about drawing it that helps get your head around it. So this is our object. We can put some dimensions on this. A free body diagram always has all the applied loads and reactions and all the dimensions. So this was 5 meters. And they told us that this was 3 meters. They gave us that the applied load here is PF. And we know that they drew this as a pin and this was a roller. A pin is restrained from moving in both the X and Y direction, and a roller in one direction has some support but not the other. There was little wheels on it in this direction, so that end can roll back and forth, but it can't move up and down. Let's label these. I'm going to call this R1X and R1Y. I'm going to call this R2Y. So we have our reactions, and we have our applied load, and we have all our dimensions. What I often find handy right away is to figure out what that angle is. I don't need it yet, but I have a feeling I'm gonna need that angle. So let's just draw that little triangle here with dimensions. This top part, this half of the top part, was 5 meters, and that was 3 meters. And remember, I always like to talk about the angle that's referenced off the x-axis. You can do it off the y-axis, but I find it's handy to just always know which one is sine and which one is cosine by having a handy little system where I always reference off of the x-axis. So this is our unknown angle here. We know that that is the opposite side and that's the adjacent side. So tangent of the angle is opposite over adjacent. Or for us, the tangent of the angle is equal to 3 divided by 5. The angle is the inverse of the tangent, 3 divided by 5. Let's take our calculator and plug this in. We can use our second function and get the tangent inverse, 3 divided by 5. Our angle is equal to 30.96 degrees. If any of you are looking at an old version of the solutions to this, that angle was wrong. The work was all right. I used the right angle, but it looks like I just input it wrong in the PDF. I'd copied it from some other solution set just because in PDFs, inputting the Greek letters and the superscripts and everything like that is very time consuming. So I'll often copy the method and put it into a new PDF. And it looks, the problem there though is sometimes you forget to update all the parts of it. Okay, so we've got a free body diagram. We know the angles. We have all of the elements named. We know now that we should be able to figure out what it takes for our reactions R1x, R1y, and R2y to make sure that this thing is in fact stable. We want this thing not to move up and down, slide back and forth, or spin. So let's start using our 3 equations. So we know for it to be not sliding back and forth, the sum of all forces in the x direction must be 0. If there was any load pushing in that direction without something stopping it, it would move. Now, I find it always handy to remind ourselves that we're talking about that direction being positive. So x is this direction, and anything in that direction is positive, meaning anything in that direction is negative. So let's sum up all the forces in our x direction. R1x, oh, that's it, R1x. R1x equals 0. That was easy, wasn't it? Okay, let's sum all our forces in the y direction. And everything upwards will be 0. Now, if you guys remember from last year, normally I don't do this equation second right here. I do the moment equation. But for those of you who are new to the course or maybe didn't do structures 1 for whatever reason, you probably find it weird that I'd go from summing the x to the moments to summing the y. That's mostly because I know the best way or the best order to solve these. But it doesn't matter what order I solve these. It makes a tiny little bit more work. So I'm just going to do it in the order that visually seems to make sense to people, but know that you could have gone right into solving the moment first here. All right, so we want to sum all the forces in the y direction. Anything upwards is positive. All right, so I've got R1y going upwards, so it's positive. I've got R2y going upwards, so it's positive. And I've got PF coming downwards, so it's negative. Wow, I have 3 unknowns here. That's a total pain in the butt. Okay, well, that doesn't give me a whole lot of solutions. So let's try the next equation that we can use, which is summing the moments about the z-axis, and we want those to be 0 as well, or we want to figure out what it takes for that to be 0. Well, if you guys remember our right-hand rule, if our thumb is pointing out of the page on the z-axis, because remember the z-axis is in and out of the page, using our right hand, you must be using your right hand for this, and you curl your fingers upwards. If our fingers are curling in that direction, our moment is positive. And if our fingers are curling in that direction, our thumb is into the page, which is a negative moment. So let's pick a point. I'm going to remind myself here that everything spinning in that direction is positive. I am going to pick point 1 here. I'm going to imagine I have a thumbtack right here. And to be a moment, you need a force and an eccentricity, or a force times a distance. So if my thumbtack is right here, R1Y passes directly through the thumbtack. It doesn't cause it to spin, so it's not applying a moment. R1X passes through that node, so it's not causing it to spin. PF is causing it to spin. It looked like it was causing it to spin in that direction. Or negative PF, and remember, to be a moment, you need a force times a distance. And moment is force times however far away it is from the point you're talking about. Well, this is the point I'm talking about, and PF is 5 meters away. Put my thumbtack here and look at R2. It's causing it to spin in that direction. My thumb is coming out of the page, so it's positive. So plus R2Y times 10 equals 0. All right, let's solve this. We eventually want to figure out what PF is, so we're going to pretend we're going to treat PF as a number we know. We're just going to call it PF. But let's rearrange this equation. R2Y, well, we can bring this over to this side and it becomes positive. So we have 5 PF, and then we can divide out by 10. We're basically 1/2 PF. Now, for those of you that intuitively looked at this and said, hey, if I have a point load here, how much goes to this side and how much goes to this side? And you said half goes to this side and half goes to this side. Yeah, you probably could have skipped all this. But we remember from last year that the easy ones are pretty easy to tell visually, but sometimes they get a little bit harder and it's not always obvious where they're going to go. So it's handy to know how to do the math. And it's always handy to start, especially even as a refresher, to start with the easy math to kind of get back into it. Okay. We can come back up here now, and if we plug 1/2 P in for R2Y, so now we know that this is 1/2 P. R1Y, we can rearrange. And it also equals 1/2 P. Okay, so we have some information now. Now, what we would always do before is we would now start using method of sections. We've drawn our free body diagram. We've solved for our reactions. Now we would start using method of sections to find these internal forces. I always like to label these elements. So let's call this, what do we want to label these? A, B, C, D, and E. So let's give ourselves these labels. They have told us that the internal force in D and E is 20 kilonewtons. In fact, they've told us it's a tensile force because TF So they said there is a tension force that it could take up to 10, 20 kilonewtons. They didn't say that's how much the load was on it, but they said it could take up to that as a reduced capacity. So let's imagine that these actually have 20 kilonewtons on them. That's really where we're going to go with this. If that's our capacity and we want to know how much load this could take, we want to go to just before these things would fail. So let's start looking at method of sections. I am going to do a section through A and D here. So we've got this here. We know that that's 0. This is something we've already solved for. And we know that this is 1/2 PF. Internal forces, remember, I always draw them in tension. It's a great habit to get into. If I'm wrong, it will actually give me a negative number, and that way a negative is always compression. You could do it a different way, but I find it easy to always draw them in tension, and that way a negative always means compression, because a negative just means we guessed wrong. If we all guessed some in compression and some in tension, it wouldn't be obvious when we got a negative. We'd have to go back and look at our starting point to see what we had made as our guess. But if we just always guess tension, we will get a negative meaning compression. So I'll call this A. And this is D. But D they've actually already given us as 20 kilonewtons. Or we could see up to 20 kilonewtons on this. Now if you guys remember, something on a diagonal is a pain in the butt to work with. So we often like to break this into dx and dy. Now they've given us 20 kilonewtons, so we can probably solve for dx and dy right away. If you guys remember, so I'm going to put away, so just to try to be consistent, I know it's a little bit hard to see in this light, but I've tried to get in the habit of always drawing applied loads in green, reactions in red, and internal forces in either blue or purple. Depends which pen I have on hand. Everything else I try to do in black. Now, that is not something you have to do. I just find it handy for communicating with you guys. In fact, you know what? I might even go back and update the solution set in that way too. Okay, so let's take a look at these internal loads over here, or these, let's take a look at this. We know we can do tip to tail. If this is 20 kilonewtons, and this is dy, and this is dx, we know that this angle here is 30.96 degrees. We know that dy equals 20 times the sine of 30.96 degrees, and dx equals 20 times the cosine of 30.96 degrees. Okay. All right, so let's take our little section here and let's start doing the same thing we did up here. Let's sum the forces in our little section. Because remember, the whole premise of method of sections is if the object isn't moving up and down, sliding back and forth, or spinning in space, neither is any section of it. Because if this section could slide off into space, the whole object should go along with it. So let's start with summing the forces in the x. Now, I'm going to admit I'm being lazy here because I can see the answer coming, but don't worry, you could go through the other steps if you'd like. Upwards is positive. I didn't mean to say X here. I'm really sorry, guys. I'm feeling very out of it. Let's sum our forces in the Y, where upwards is positive, and let's see what happens when we sum the forces in the Y. We've got 1/2 PF going upwards, which is positive, so 1/2 PF upwards, and the only other thing is we've got the component of this tensile force downwards, or dy. It's downwards, so it's negative. dy we see is actually 20 sine 30.96 degrees. Those are the only forces in the y direction. Look at this. We have one equation and one unknown. Remember, the whole point in this was to figure out what the maximum PF we could apply to this was. So let's rearrange this. We can bring this over to this side and it becomes positive, and we divide by 1/2. PF equals, let's plug it into our calculator here. We've got 20 times the sine 30.96 divided by 0.5 equals 20.6 kilonewtons. So this truss could support a point load of 20.6 kilonewtons without overloading these bottom chords. Change the shape of this in any way and you will get a different number here. So we could go find all the other internal forces in this, but the goal was to find out what the maximum load we could the maximum load we could apply right here without overloading this system. And it looks like for us that is 20.6 kilonewtons. Okay, I'm going to start this and prep to do the next question. Okay, let's look at the next problem. So this is one where they're saying the building department is asking for a calculation report on a specific roof beam. Now, this actually happens quite a bit. We'll have a massive project and the building department will say, I'm going to pick this beam and this column and this base plate and this footing, and you're going to provide a calculation report for me. Oddly enough, they tend not to ask about the hard things, but that's a separate issue. So they're asking explicitly for a calculation report on roof beam 01. We've been told this is a communications hub. Now, last term we didn't do any post-disaster calculations really, but just to mix it up a bit, I thought I'd show you some of the hardest things we could do. So a communications hub, falls into post-disaster construction because it's an essential service building. It needs to, I always think of it as, it needs to survive the apocalypse. So a regular building, just you want everyone to get out alive in a disaster. A high importance building, we don't need it to function as it's intended after a disaster, but it needs to be standing after a disaster so people could go use it as a shelter, for example. So a community center would often be post-disaster unless we've been told otherwise. It would be high importance so that it can be used as a shelter after a disaster. Post-disaster are the buildings that need to be able to function as they were intended even after a disaster. So hospitals, communication hubs, ambulance deployment buildings, police stations, fire departments, all of those would be post-disaster building. So it does not have finishes susceptible to cracking, so it's not a precious building inside, so there's no drywall, there's no plaster. It's probably just an exposed ceiling with insulation on the roof. So We don't have to worry about cracking. We can follow whatever guidelines that is. There is not a building directly adjacent to it that is higher, but that doesn't mean there are no other buildings beside it. So that means that it's still it doesn't have wind scour on the roof, but it's not going to have ASL. It's not going to have accumulated snow loads on this roof. The 1 in 50 year climatic data gives SS as 2.1 and SR as 0.3 kPa. So they've gone and looked up this information for us. Normally, we'd have to know where this building is, and we'd go to our data sheets for climatic data and look up what SS and SR is so that we could find the design snow load that we would use. And we would need the one that we will use in our factored load cases and the ones that we would use in our serviceability load cases. So here's RB01. So this is the beam that we're going to be talking about right here. And we need to design this whole beam. Now normally we would need to make sure that the factored shear and the factored bending are less than the reduced capacity shear and moment for a particular beam here. We only know how to do half of this. So we need to find the internal loads on this beam. So what else have they told us? Let's see exactly what they've asked for. They've told us we know what the roof assembly is because we've looked at the drawings. And the building department has given you a list of things they'd like to see. The dead load, the snow load, the factored load, these are all in kPa. Calculate the line load on the beam. And it says tip, treat the load as a uniformly distributed load. Draw the free body diagram of the beam supporting the joists. Calculate the reactions. Draw the shear diagram using method of sections. Draw the moment diagram, use method of sections. And determine the maximum allowable deflections. And identify MF and VF. So that would be the maximum shear and the maximum moment. Verify with equations from beam loading diagrams. Now, I'm going to tell you that most of the time we just jump to this part right here. After today's lecture, you are never going to have to do method of sections unless you need to again, but I am not going to be assigning method of sections after this point. But it's handy to know how to do it because a lot of the thinking that happens by doing method of sections we will still use. So the very first thing is let's determine the dead load. Well, it looks like they've given us the assembly right here. So let's write this out. So first thing first, section A is our dead load. Let's make me bigger here. All right, the very first thing is determine the dead load. So we know we have 3-ply asphalt. We have 102 millimeters of concrete topping. Now there's nothing here to tell us that it's fancy concrete topping, so if all things being equal with no other information, we would assume that is normal density concrete. 6 inches of rigid glass fiber insulation, 8 inches of hollow core. Our steel weight, they've given us an assumption, mechanical and electrical. And a suspended ceiling tile. Now, this one's clearly not precious and they don't care about cracking. Normally, I would probably include a suspended tile as a finish, but they've said don't worry about it, we don't care about it in this situation. So let's go to our dead load charts. So this is available on Quarkus in several module locations, but these are the design dead loads for different materials. So the very first thing they asked us was about 3-ply asphalt roofing. So let's come over here to roofing materials. 3-ply asphalt with no gravel. There was nothing that talked about gravel in our description, so this looks like it's 0.15 kPa. 102 millimeters of concrete topping. Well, there's steel decks here. Concrete per 100 millimeters. Now, if this was concrete on metal deck, we wouldn't take this and try to solve it. For concrete on metal deck, they have deck slabs, which is metal deck with a concrete amount on top of it. But that's not what we have here. We have just plain old concrete. And this is per 100 millimeters of concrete. And they've given us a weight for normal density concrete. Now this says 2.31 per 100 millimeters. We're working in imperial, so I'm gonna stick with this. I'm gonna use 102 millimeters here. So I'm gonna take my 102 millimeters divided by 100 millimeters and multiply it by my 2.31. And I'm gonna get 2.36 kPa of concrete for the metal, or for the concrete weight for the concrete topping. The next thing they said was 6 inches of rigid glass fiber insulation. All right, insulation, here we are. Per 100 millimeters thick, we have 6 inches, and it was glass fiber rigid. So every 100 millimeters is 0.07. 6 inches is 152 millimeters, divided by 100 times 0.07. We're going to get 0.11 kPa of glass fiber rigid insulation. The next thing is 8-inch hollow core precast panels. Well, they have hollow core precast here. So these are, if you guys remember, I said it's ubiquitous. They go back and forth. You don't have to do any calculations. The 8-inch is the 200 millimeter deep. Even though they're calling it 200 millimeter deep, it's normally 8 inches. And I said, so don't even do anything. You just flip back and forth between them. So our 8-inch hollow core precast with no topping, because we added the topping ourselves, is 2.6 kPa. All right, the next thing is our steel, which they told us is to assume 0.2 kPa. Mechanical, electrical, if you guys remember, in ceilings there was a ducts, pipes, wiring allowance, average condition is 0.25 kPa, and that would be standard unless you had a good reason not to. And while we're in ceilings, there's suspended tile. So tiled ceiling and suspension system with fixtures average is 0.2. So it looks like we have all the elements that make up our roof here. Let's add these all up. So we have 0.15 plus 2.36 plus 0.11 plus 2.6 plus 0.2 plus 0.25 plus 0.2 equals 5.87 kPa. So our total dead load. All right, it looks like we've solved part A. Question B was our snow load. Now, if you remember, they gave us a few things embedded in the question. Let's just start by writing out what the snow load equation is. If you guys remember, our snow load equaled our importance factor times SS times CB times CW times CA times CS plus SR. So we need to figure out what all of these things are. All right, let's talk about IULS and ISLS. IULS is the importance factor for our factored load cases. And for a post-disaster building with snow, our importance factor is 1.25. That is a chart that I have given you, and it's available on Quercus. And our importance factor for serviceability for snow is 0.9. SS we were given as 2.1 kPa. SR we were given as 0.3 kPa. Now these two things would be looked up in the climatic data, so we would have access to those by looking at the climatic data in Ontario. The other things we need to figure out are our factors here. Now, CW is about our wind scour, essentially. Now, we said that there are no buildings taller than it, but that doesn't mean there's not buildings around it. To be able to wind scour, you need no buildings, or you need no obstacles around your building for something like a kilometer away. It's almost impossible to have anything but one. I've rarely used less than one for that. Oh, we forgot CB. If you guys remember, CB is just the factor that we apply because we're talking about a roof rather than the ground. The loads they've given us here are the ground snow loads. CB means that it's up on the roof. At least a certain amount as it falls down comes off of the roof. If you have a gigantic roof, like a warehouse or something like that, CB can start to equal 1, but usually only in the interior of the building. So I've done some very large community centers that were 1 story and they had 2 rinks and 2 swimming pools. So it was a gigantic roof plan, and some internal portion of that roof had a CB of 1. But for you guys, you're not going to worry about it. It's going to be 1. CA is our accumulation factor. Now, we don't have any buildings around it that would cause accumulated snow load to pile up on our building. It didn't say anything about a parapet. We would worry about a parapet if it was there, but it didn't say anything about it. And then CS is our slope. It didn't say it wasn't a flat roof. It looked like a flat roof looking at the design of it. So I doubt there's any way we could slide any of the snow off that roof. So it looks like we have all of the information we need. So let's calculate our snow load for ULS calculations and our snow load that we'll use for our SLS calculations. So for our ULS calculations, it's going to be 1.25 times 2.1, which is going to be multiplied by 0.8 times 1 times 1 times 1 plus our 0.3. Now, the 1.25 gets multiplied after we do all of this. And for our snow load, or for our serviceability cases, everything is the same except our importance factor. So I can plug this into my calculator. 2.1 times 0.8 plus 0.3 is 1.98. So 1.98 times 1.25 is 2.47 kPa, and 1.98 times 0.9 is 1.78 kPa. Okay, what was the next thing they asked us to do? They asked us to determine the factored load on the roof in kPa. So the factored roof load in kPa. Now remember, this is the different load combinations we would need to see. Remember that we have a bunch of different load combinations. It gets a little bit easier when there's only 2 loads applied to it. Now, for those of you that are sticklers for the rules, there is a clause in the code that for a roof load, you do need to consider a live load of 1 kPa. But it also states you don't have to do it in conjunction with any other load cases that aren't dead load. If it's 1, it's always going to be less than the snow, and you don't have to do it with companion loads the way you would most other load cases. So it does not need to be taken into account with companion loads. So we don't tend to worry about it unless there's a specific reason to. All right. We're going to have our ultimate limit states load combinations. And remember, I always put a little U in front of it to remind myself of all the combinations I'm thinking of. And we're going to have our ultimate dead case we're going to look at, our ultimate dead snow, and we know that there's a companion load of live that we'd need to worry about on there, and ultimate dead live snow, with live as the main case and snow as the companion. Now, here's the thing, we have no live load. So live load being the primary load case, I'm not even going to calculate it. There are conditions where this might not be as apparent. If we have multiple stories in our building and there's live load being applied to the second floor, but it's also carrying snow load from the roof on a column, for example. So for our factored load cases, we've got 1.4 times our dead load of 2.47, of 5.87. And for our dead and snow case, we've got 1.25 times 5.87 plus 1.5 times 2.47. Let's plug these into our calculator. 1.4 times 5.87 is 8.22 kPa, and 1.25 times 5.87 plus 1.5 times 2.47, 11.04 kPa. So that means when we're designing our roof, the worst case is going to be this condition right here. So our ULS load case, so our factored load is going to be 11.04 kPa. Now, we know that we have some deflection calculations we should do here. Let's take a look at, and this is where I always suggest tracking everything. Let's look at our serviceability dead and snow and our serviceability snow. Well, that is just adding up our 5.87 plus our 1.78. We've already included our importance factor here. So this one's pretty easy, but I like to just keep track of these because it's going to be handy later. Now, I don't know if you remember, this is one where we do not look at the worst case. We have to track both of these because we have two different deflection criterias. Now, sometimes it'll be very obvious which one governs, and sometimes it won't. I suggest you always keep track of them, and so you use them, so you have them when you need them. Okay, the next calculation is calculate the line load on the beam, and we're talking about, I believe it's 2BO4, and it says treat the load as a uniformly distributed load. Okay. Let's take a look at this beam here for a second. So it's RBO1. There's its length, so we can see that it's 10 meters. This RBO1 looks like it's picking up half of the load that these RJO1s would apply to it, and half of the load from these RJO1s. That is 8 meters, and that is 8 meters. So 4 meters from this side would load up this beam, and 4 meters from this side would load up this beam. So it seems like we're saying it has a tributary width of 8 meters. It's interesting that it was the last one. So the next question was, let me see here. So D, we want the UDL, or the uniformly distributed load. Now, this does not mean the factor dead and live load case, but we want the UDL on roof beam 01. Or sometimes you'll see me call it WF. And WF is the roof load times the tributary width. And so we've got a tributary width of 8 divided by 2 plus 8 divided by 2, or 8 meters. Because that beam is picking up 4 meters from one side and 4 meters from the other. So our uniformly distributed load on this is going to be 11.04 times 8 meters. Let's calculate this. We've got 11.04 times 8 is 88.3 kilonewtons per meter. So what we're saying, along every length of this beam, it's supporting 88.3 kilonewtons. Let's look at our W dead and snow, or serviceability dead and snow, and W serviceability snow. Just because, remember I said it's nice to keep track of these things. 7.65 times 8 and 1.78 times 8. So 7.65 times 8, 7.65 times 8 is 61.2 kilonewtons per meter, and 1.78 times 8 is 14.2 kilonewtons per meter. Okay, the next thing was E. They want us now draw the free body diagram. So we want the free body diagram of roof beam 01. Well, first things first, we knew that it was 10 meters. So 2, 3, 4, 5, 2, 3, 4, 5. So this is our beam, and we know that it is 10 meters long. We just calculated that it had a uniformly distributed load on it of either WF or W serviceability dead snow or W serviceability snow. depending on which condition we're talking about. And this was 88.3 kilonewtons per meter. This was 61.2 kilonewtons per meter. And this was 14.2 kilonewtons per meter. We know there should be something stopping this from going up and down, back and forth, and spinning in space, or else it is not stable. We've not met the very first criteria of strength, stiffness, and stability. If it's not stable, everything else is useless. Why would we even bother? This beam is going to come crashing down. So we need to figure out what makes it stable. We know that most beams are simply supported. When we looked at that drawing, let me just sneeze again. When we looked at that beam, RBO1, it doesn't look like there's any moment connections at the end. And we know that for a typical beam, if it's in normal construction, it has the ability to move just a little bit at the ends, just enough to release our reactions at the end, which means most beams are typically a pinned roller condition. So we've got R1X and R1Y and R2Y. So we have our applied loads, our reactions, and our dimensions. So we've got our free body diagram. All right, step F was reactions. They wanted us to calculate the reactions. So we know that once we have a free body diagram, this starts to get pretty easy. We can sum the forces in the y direction, sum the forces in the x direction, and spin it about whatever point works for us. But here's the problem. It's a pain in the butt to do it with a uniformly distributed load like this. What we'll often do is do a temporary free body diagram to help us solve this using an analogous point load. This is not the actual free body diagram. So we're going to use a temporary free body diagram. And I'm just going to draw it at half scale here. So this is a temporary analogous point load drawing. So this is still R1X, this is still R1Y, this is still R2Y. This is still 10 meters, but this is our analogous point load, PF, which is the length times our load, our uniformly distributed load. Remember, we're saying that every meter along this beam is supporting 88.3 kilonewtons. So this has 88.3 kilonewtons, this has 88.3 kilonewtons, this has 88.3 kilonewtons. So the entirety of the load of it is our 10 meters times 88.3 kilonewtons. I don't think I need a calculator for this. 833 kilonewtons. Okay, I'm just going to do it with the factored loads for now. We'll come back to anything else we need in a little bit. So we want to calculate the reactions on this. So let's use our handy 3 equations. We are going to start by summing the forces in the x direction, where everything in that direction is positive. And we want to know what it takes for this to be in equilibrium. Well, we've got R1x equals 0. That one's always the easiest. Let's sum our moments about the z-axes and see what it takes for this to be in equilibrium. Everything's spinning in that direction with our thumb out of the page using our right hand is positive. And let's pick this point right here. I'm going to pick node 1 to spin everything about. All right, so if I put my thumbtack right here, R1y passes through it. You need a force times a distance to have a moment. R1x passes through it. PF makes it spin in that direction. My thumb's into the page, so it's negative. So it's minus 883. And to be a moment, you need a force times an eccentricity or a distance. So this is 5 meters. All right, put our thumbtack here. R2y causes it to spin in that direction, which is positive. So plus R2y times 10. We can rearrange this and solve for R2y. And R2y is, we bring this over here and it becomes positive. So 883 times 5 divided by 10 equals 441.5 kilonewtons. Intuitively, you probably knew that. If we had 883 kilonewtons on this, we know that half of it's going to go to this side and half of it's going to go to this side. The same way that when we looked at this, we knew half the load would go here and half the load would go here. So we have R2y. Intuitively, I think we can figure out that R21 is going to be the same value, but let's go through it. Sum the forces in the y direction. We want everything to be 0 or else this thing's going to move and it's not stable. Remember, moving is different than deforming. Upwards is positive. We've got R1y minus PF, which is 883. So R1y is positive. PF is downwards and it's negative. R2y is upwards and it's positive. So plus 441.5 equals 0. We rearrange this. And R1y, we bring these over. We get 883 minus 441.5, we get 441.5 kilonewtons. Okay, so we've solved F. G, draw the shear diagram of the beam. Use method of sections. Draw the moment diagram of the beam and use method of sections. So I'm going to kind of lump together G and H here. So G and H. Shear force and bending moment diagrams. Now, they have explicitly told us to use method of sections. I mean, at this point, after this, you don't really have to do it that way. You can look at the very handy table of beam loading diagrams I've given you, which shows you with a particular load on it what the loading diagrams will look like, or the shear force or the bending moment diagram will look like. But we're going to go through it the proper way just for now. I am going to do it again with placeholders here. So we are going to draw a section somewhere through this beam. We're going to have an unknown amount of this beam. We're going to draw a line through it. We're going to take a section of it. In method of sections, we know that if the object isn't moving up and down, sliding back and forth, and spinning in space, then the section of it isn't either. So let's draw my section. So I've got some section of it here. I'm going to call this distance x. I don't know how long that is, but it's somewhere along this beam. I've got my applied load WF on it, and I know that I have these reactions. We've already solved for that one as 1, and this one is 441.5 kilonewtons. For this not to be moving around in space, there must be something holding it in place at this end. There has to be something. And we know that at this section, there's the rest of the beam. So there must be internal forces here between this part of the beam and the rest of the beam that's holding this part of the beam in place. I'm going to use a placeholder V and a placeholder M. I don't know what these internal values are. Now, we are using factored loads here, so we can call these, we can use the subscript F here. Because this has the subscript F, any values we calculate here will have the subscript F because they're factored. Well, this also still isn't that handy. Let's again, so this was the free body diagram. Let's do a temporary free body diagram of this now. So 1, 2, 3, 4, 5. This is still x meters. Instead of the uniformly distributed load, I am going to use a PF here, and it is this distance times the load. Well, we know that WF was 88.3, and so PF is 88.3 times x, because this meter had 88.3 kilonewtons on it, this meter had 88.3 kilonewtons on it, this meter had 88.3 kilonewtons on it, but we don't know how many meters we have, so we'll use that as a placeholder x. We still have our reactions of 0 and 441.5 kilonewtons. I should write that this is kilonewtons here. And then we have unknown internal shear force and unknown internal moment force. I can't believe my kids are still asleep. It's 7:30 and they're still asleep. I'd like to get through this problem before I stop this. Okay, let's solve for, let's start using our equations. So let's, so between 0 and x, let's sum our forces in the y direction. So everything upwards is positive. Well, let's see what we've got here. We've got 441.5 kilonewtons going upwards. Downwards, we have, which is a negative, 88.3x. So that's our force, is 88.3x. And also going downwards, we have VF. Well, we can rearrange this. VF is what we care about. Let's rearrange this, and we can bring this over here, and we have 88.3x minus 441.5 kilonewtons. Let's sum the moments about the z-axis, where everything in this direction is positive. And I always, when I'm doing this, pick the point x where I've cut it. Remember, anything passing through the node that you put your thumbtack doesn't cause a moment. If it's a force passing through it, it doesn't cause a moment. I usually do it here because it gets rid of VF for me. I don't have a weird thing and a weird unknown in it. You can still solve it any way you'd like, but this I find is the quickest way to do it. So we have a thumbtack right here, which means we have 441.5 spinning it in this direction. So it's trying to turn our page like this. So it's spinning it in that direction. So my fingers are curled in that direction, so it's a negative. We have minus 441.5. To be a moment, it's a force times a distance. So we've got 441.5 times x, because it's x distance away. Our VF passes directly through it, so it doesn't cause a moment on it. PF tries to spin it in this direction. My thumbtack's right here. It's spinning it in this direction. So it's a positive value. So plus 88.3x. And to be a moment, you need a force times a distance. If this is x, this is 1/2 x, or 0.5x. Our moment, we don't know what direction it's in, so we're assuming it's in the positive direction. So plus mf equals 0. We can rearrange this, and we get that mf equals minus 44.1 x squared, so that was this here, plus 441.5 x. Okay, so anywhere along x, we can solve for VF and MF. Let's take a look at what that looks like. Let's make ourselves a little chart and pick a few points along this beam. I usually find it handy at this point to make a little chart. All right, so at x equals 0, x equals 1, x equals 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that VF equaled 88.3x minus 441.5, and MF equaled minus 44.1x squared plus 441.5x. Let's figure out what VF and what x is, or MF is, at all of these points. All right, let's maybe just go through and do all the VFs first. So we have 88, well, let's do it at the beginning just because it's easier. So 0 times 88.3 minus 441.5. Oh, sorry, I wrote this down wrong. Yeah, sorry, guys, back here. I just did one funny thing here. I changed the signs of this, but this was already a negative, so I actually should have just brought this over. So that's the negative, and that's the positive. It doesn't change any of the numbers. It just flips which side is which. So this is minus, and that's plus. I thought something seemed a bit funny there. So 0 times negative 88.3 plus 441.5. We get 441.5. Let's do the same problem, but with 1 there. We get 353.2. 264.9. 176.6. 88.3. Oh, at the halfway point, it's 0. Oh, look at this. It starts to flip and go up. You can plug these in and you'll see this is correct. Had I kept these the opposite way, all of this just would have flipped. Remember I said in shear, positive or negative doesn't actually have any real meaning. The reason we like to keep track of it is it tells us when it flips the axes, when it goes from one side to the other. So we need to keep track of it just so we can see where we cross the axes or where it hits 0. But whether this side was negative and this side was positive, or this side was positive and this side was negative, is irrelevant. I tend to consistently do it so that the left-hand side of my equation is positive. But it's not something to get too fussed up over. All right, let's calculate our moments. So negative 44.1 times 0 squared plus 441.5 times 0. Oh, that's easy. 0. Now, you guys can go through and plug this into your calculator. I've already done it and written it out here just so I can start to fill this in faster. You feel free to plug these into your calculator. I know I'm on borrowed time before those kids wake up, or at least one of them. Look at this, at the 5 mark, it looks like it peaks, and then it starts to go down. Okay, we plug that all in. Now let's draw these diagrams that they've asked for. So shear force diagram. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. We went up to 400 and down to here, and this was 0. If you plotted all of those points on here, you would see that this was a nice straight line. I usually like to color this in just so it's really obvious. I always indicate that this is in kilonewtons, and this is 441.5, and this is 441.5. Remember, once we're talking about it in the diagram, positive and negative is almost irrelevant for our shear force. Okay, so bending moment diagram, and it is in kilonewton meters. So all right, so here's our datum line. We go up to here, and we know this is 0 and this is 0. What's interesting though is that it is not a circle. I guess that's even lower. It is a quadratic equation. So this is not half of a circle. it is a quadratic equation. So it drops off more rapidly as you get closer to the supports. The worst case moment is at the middle. And it is a value of, we calculated that as 104 kilonewton meters. Okay, there was two other things it asked us to do. I am going to just right here identify question J. So question J said identify MF and VF as the maximum values. So VF max is 441.5 kilonewtons, and MF max equals 1104 kilonewton meters. Now, these don't occur at the same location, but we need a beam that has a reduced capacity of shear greater than that and a reduced capacity for moment greater than that. And that's what we're going to embark upon this term. There's one more thing they asked us to do, and that was the allowable deflections. So this is a steel roof with elements not susceptible to deflection. Let me pull up our deflection chart, our serviceability limits. So roof, snow and dead, both of them, not susceptible to finishes. And we have for steel, L divided by 360 and L divided by 80. It looks like in my example, I forgot that I had written not susceptible to finishes. Just going to double check that I did in fact write that. Does not have finishes susceptible to cracking. Okay, so I'm going to rework this. I'll fix this solution for you when I post it. So it looks like I had assumed finishes that were susceptible to damage at first. So we know that the deflection that's allowable for dead plus snow is L divided by 180, and the deflection allowable for just snow was L divided by 300. Hey baby boy. Hi. So I have one quick thing left and then I can hug you, okay? So let's see what the allowable deflection is for these. Remember, our length is 10 meters. So deflection allowable for dead plus snow is 10,000 divided by 180. And our deflection, I'm almost done here, baby boy, is 10,000. How do you feel? How do you feel this morning, Duncan? You feel good? Okay.
Yeah.
Your brother didn't feel good this morning. Okay.
Yeah.
So 10,000 divided by 180. And we have an allowable deflection of 55.5 millimeters. And for just snow by itself, we have 33.3 millimeters. So there, we've done all of the things that the building department has asked us to in this example. So I'm going to take a break here. I'm hoping I'll get to record more today. If not, everything's all been worked out. I'm going to fix those and post them for you. And hopefully this will be a longer lecture than this. If not, you've got lots to work through.